Hey everyone, it's Justin again, and welcome to the second portion of our quadratic functions unit. The solving skills you've mastered in the first section of the unit will come in handy again soon, so be sure to keep them fresh in your mind. Next, we get to focus on actual quadratic functions. Yes, functions with two variables. You know, those things that can be graphed on a coordinate plane. Quadratic functions create a certain U-shaped curve when graphed. That's called a parabola, or a parabolic curve. So what characteristics do quadratic functions, or parabolas like these, have? Well, let's find out. Identifying the characteristics or attributes of a parabola will involve using a lot of vocabulary. You've seen a lot of it before, like y-intercept, x-intercepts, domain, range, increasing interval, and decreasing interval. But some of these terms may be a little less familiar to you, such as vertex, axis of symmetry, and maximum or minimum. Today, we're going to make sure you can identify all of these parts on a quadratic functions graph, or a parabola, and some of the relationships between them. This lesson's guided notes contain two parts. The first part will give you a chance to review the concepts you've already learned in this course and apply them to this new type of function, and the second part focuses on the new concepts that you haven't seen yet in this course. Then we'll do an example problem to ensure that you're ready to apply these concepts in different contexts. Let's start with part one. For this section, I need you to take the lead and complete part one of your guided notes. Once you've finished, come back here and I'll give you a chance to check your work. Pause the video and do this now. All right, how'd it go? Let's check your work. You should have a y-intercept of 0, -1 for this parabola. And for the x-intercepts, you should have actually found 2 of them for this first graph, 1 x-intercept for this middle graph, and, well, none for this last graph. The fact that quadratic functions can have either 2, 1, or no x-intercepts at all is something we haven't seen before in this course. This is not something we had with linear and exponential functions. Next is domain and range. Since these can be written using inequality and interval notation, we have a domain of -infinity to +infinity, which can also be written using the all real numbers symbol, and a range of everything -3 and higher for the first graph. And for the second graph, we have a domain of all real numbers again, and a range of everything less than and including 1. The last topic from part 1 of your notes are the increasing and decreasing intervals. For the graph provided, we have an increasing interval up until an x value of 3, and then when we go past 3, this is decreasing. Great job so far. It's nice to know that some of the topics we've already learned about in this course apply directly to quadratic functions too. Now, if you got anything wrong or want some more explanation on anything, there is a help video link in your PDF that you can watch. Now's a great time to pause this video and take a look at that video if you'd like to. Next, let's learn about those remaining attributes that you'll be working with. These attributes are in part 2 of your guided notes. These are more specific to quadratic functions and are probably new to you. Let's check them out together. Our first new term is vertex. Knowing that linear functions and exponential functions from earlier in this course don't have a vertex, do you have any guesses as to what a vertex could be? Parabolas have a portion of their graph that increases and a portion of their graph that decreases. And the vertex is right in the middle of those, like this. It's the highest point, or maximum, on a parabola that opens downward. What about a parabola that opens upward, though? Where do you think the vertex is here? Yeah, the vertex is the lowest point or minimum on a parabola that opens upward. So on this parabola, it's right here. It's important to be able to identify the vertex and state whether the vertex is a maximum or minimum. So on both of our examples, let's be a little more specific and state that the first parabola's vertex is a maximum and the other one is a minimum. Our final attribute is the axis of symmetry. What does the word symmetry or symmetric remind you of? Maybe you are thinking of a mirror image of something, or when a line can split something in half and both sides are a reflection of each other. Do you think you could draw a line of symmetry on this parabola? If so, what would the equation of your line be? A line here would show symmetry from one half of the parabola to the other, and the equation of that line is x equals 3. This line is an axis of symmetry, which is a vertical line that splits the parabola into two identical halves, or that shows a mirror image of one half of the parabola onto the other. A nice feature of parabolas, because of their symmetry, is that any point on one side of the axis of symmetry will be the same horizontal distance from the axis as another point on the opposite side. The axis of symmetry will also go through the parabola's vertex and utilize the same x value, which in this case is 3. Now, what do you think the axis of symmetry is for this parabola? For this parabola, the axis of symmetry is x equals -2. Maybe you even verified that this is correct by checking that some points on the parabola are the same horizontal distance away from it, like this. Or by noticing that it goes through the vertex, which also has an x value of -2. All right, now that you've learned about all the attributes you'll be working with for quadratic functions, it's time to try an example problem where you'll put these concepts into action. This says, given that a parabola is decreasing from -infinity to 1 and increasing from 1 to infinity, fill in as much as possible for each attribute listed below. What do you think we could do first on a problem like this? I think having a sketch of what we're working with could be very helpful. So let's start by making one. All we really know here is that the parabola is decreasing on this portion of the graph and increasing on this portion of the graph. We don't know how narrow it is or how wide it is, and we don't know how high up it is or how low it is on the graph. But even so, there's still a lot we can say about these attributes with just this small amount of information. To help us visualize some of the options, let's go ahead and record a few possibilities for what this graph could look like. I'm going to sketch in these 3 parabolas as examples. Go ahead and record a few possibilities in your notes as well. Now that we have some visuals to help us reason through this, let's see what we can fill in for each of these attributes, starting with the vertex. Is there anything that the vertices on the sketches you created have in common? They aren't necessarily all in the same place, but do you notice anything that is the same for all of them? You may have been thinking that they're all minimums, or that they all have an x value of 1. Would these things always be the case for a parabola with these decreasing and increasing intervals? Yeah, so let's record these things as something we know to be true. All right, go ahead and take it from here. What else can you fill in for these attributes with just the little bit of information we were given in the problem? Pause the video and see what you can come up with. Use your sketches to help you reason through this. Let's talk about the domain. What is the domain for all the parabolas you sketched on your paper? And all the parabolas I sketched? Yeah, their domain is all real numbers. No matter where a parabola is or whether it opens up or down, unless we restrict it, the domain will always be all real numbers. I'll use inequality notation to represent this, but interval notation or the all real numbers symbol are great too. Now, what about the range? Since the original information tells us the parabola decreases and then increases, we know the parabola opens upward. How does opening upward affect the range? We know it will go up to positive infinity. Do we know how far down it will go? No, that we don't know. So let's leave that part of the range blank. Last is the axis of symmetry. How does the axis of symmetry relate to the vertex again? Yeah, it goes through the vertex. If the vertex is 1 comma something, how will that connect to the equation of the axis of symmetry? We can use the x value of the vertex to write our equation. We had 1 as the x value of the vertex for any possible parabola that fulfills the initial description. And the axis of symmetry is x equals 1. Great work on this example problem. We weren't able to fully figure out every attribute with the information we were given, but by sketching our own possible graphs and using our reasoning skills, we came up with a lot. Remember to sketch your own graphs to help you visualize possibilities based on the given information when you do problems like this. It's a great approach to use, and it can be really helpful. And there we have it. Nice work today with your guided notes. There are 2 activities in your PDF that you'll want to check out next. Then you'll be ready to complete the online practice. Good luck with that, and I'll see you next time.